2 minutes till official start time. All right. I think we're still missing 2 people, but we'll go ahead and officially start. So if you saw me this morning, then you at least know my name. So I'm Marissa Shepard. You can just call me Marissa, that's fine. And so I have a PhD in chemistry, so it'll be in good hands with me. We'll hopefully have some fun in here. So let's start off with the roster. So I only take attendance on the first day, that's just to see who's here. And then there are people that are missing the recitation section, so we'll kind of go over that, and I'll give you the codes. So if you're missing stuff, you can add them. All right, so let's start with Abigail Adams. No, didn't make it over here. Okay. Micah. You're Abigail, right? Yeah. Okay, just checking, because I saw you this morning, and sorry, I'm kind of bad with faces and names, but just give me a little bit of time. Sophia. No, Sophia? Okay. Gracie. So you're in lab, you're here. Ayla. And if I butcher your name, let me know. Sadie. Here. And then I believe Ryan dropped with a K. I just want to double check. Okay, so that was probably true. Ashley Lee. Ada. Is that how you pronounce it? And if you have an alternative name, you can let me know. Michael. Or if you want to be called whatever. Olivia. Okay, you're in lab. You made it. Bianca. You made it. Alexis. Awesome. Ethan. Thank you. Trinity. Mackenzie. There you go. Elizabeth. And Leslie, where you at? Bethany, you were here this morning. Ellie. And Georgia. Perfect. All right, I think we have almost everybody. Excellent. All right, let's go over those sections before I forget. So it sounds like everybody's enrolled in this lecture, but let me pull up the course code just in case. All right, so the Chem 104 lecture, so again, I assume most people are enrolled, so that's PXTQ. And so we have plenty of space in both labs, just FYI. And so like Wednesday people, that's where you might have to plan ahead. So, if you know you have some sort of obligation on Wednesday, you are more than welcome to come in on my Monday class. And so I don't think there's an issue with the labs, but I'm going to put the code up just in case. So we have Monday lab, 9 to noon, so that happened. People were there. That went well. So ENBW, if anybody needed to officially change their schedule, that's fine. But again, it doesn't really matter too much which lab you're signed up for, just as long as you show up. There's a lot of flexibility since the labs are only like half capacity. And so the Wednesday one, so if you didn't come to Monday, I hope to see you on Wednesday at 9 a.m. So that's LWBF. And then, so you have to sign up for recitation. And I notice that's where I'm missing the most people. So eventually I'll look through my roster and send people a nice email. But if you haven't registered, just go ahead and do that. So it's just part of the same 5-credit package deal. So that's why you have to sign up for lab lecture and recitation. And all recitation is, it's specifically for like math, physics and chemistry, where there's a lot of math involved in the subject inherently. So it's just an extra space for practice. And usually I use that time on Wednesday as I give our quiz then. And so we'll go over the syllabus and kind of the format of the class, but basically every Wednesday during recitation, you'll have your quiz, and then the rest of that time is like usually yours to ask questions or do whatever. And so the code for the Wednesday recitation is HPQ QP, so make sure you sign up if you're not enrolled. And so they try to fix it with like block scheduling so that your lecture portion is always 1 to 3, either Monday or Wednesday. And so that's why you have that weird like schedule where it says like lecture on Wednesday is only 2, like 1 to 2 or something, and then recitation is 2 to 3. So it's just all one big block. Does that kind of make sense? So you're not signing up for extra classes or extra work with this recitation. It's just space, really. But yeah, you're required to sign up for all 3. Unless you have some weird scenario, but then you would have already talked to me. All right, so let's do a quick navigation. Oh man, I screwed up. So probably somewhat familiar. So you have your syllabus here. So your syllabus is your best explanation of assignments. And so I would really just look at these week assignments, but you can kind of see they're very repetitive, right? So we'll have labs, you'll do your lab. I have the sheets for you. Right now I'm still not doing like pre-labs or anything, so you don't have to stress out about that. You just do it when you get to lab or whatever. I'm not checking that. But you notice each week we have a lab, and then basically they'll be due the following week. So if you have the Monday lab, you can turn it in the next Monday, Wednesday lab, the next Wednesday. But as you'll find, I'm pretty lenient with dates and deadlines as long as it doesn't get out of control. You know, I understand that you might have a lab, maybe you don't understand the math, you need some help with it. I'd rather you turn it in late and get help from me. And again, I'm not going to penalize you for being late. I'd rather you get help and get it all sorted than you're just trying to like rush and turn in assignments. But of course, that being said, right, you got to kind of keep pace, because I don't want all 20 of you handing in an entire term of assignments right at week 10. Like at that point, I can't physically grade, but I try my very best to accommodate everybody. I understand, you know, life happens, and I want everybody to have that. And so we'll kind of follow this. So I'll hand out homework. So every week I'll have homework for you. I'll have labs, or again, if you had the Monday lab, you'll probably be seeing that lab first thing on Monday. And any other handouts will be there for you, and I'll pass them out. But then you'll have your homework, and your homework, I believe, if I did it correctly, sometimes I forget. Oh, see, I forgot. So I'll add that. But there should be a homework assessment. I'll do that later. So you can either turn in homework online on Blackboard, or you can just physically hand it in to me. Either way. So if you hate Blackboard, you never really have to look at it. And so again, you'll have a quiz. So we won't have our quiz. Our week 1 quiz will be next week. So we will have a quiz this week, but it's going to be a welcome assignment. So, you know, just like, why are you taking this class? What are you interested? So no studying. But if you're not going to be here on Wednesday, I might have you take it today, just so I have an account of who's here. But if you're going to be here on Wednesday, we'll just say that for Wednesday. So that'll be our quiz this week. But then, right, next week, we'll do our Chapter 1 quiz. The subsequent week, right, Chapter 2, so kind of so forth. It just follows, and then you can see, right, when we have our exams. And so they will be on that Wednesday. So they'll start during lecture and then take over recitation, so you have a nice long 2-hour block. And if you have accommodations or anything, you know, we could also just extend the time for that. And we'll have labs, so pretty self-explanatory. And so your grades, oh, come on. Did I forget to put the grade in here? Oh, here we go. I was looking for the weighting. So your grade is based off of, so exams, 50%, lab reports are 20%. So we'll have a lab practicum This isn't something to stress about. It's, just like what have we done in lab, some basic stuff. So that'll be part of your grade. And if you look on the syllabus, so that will be at week 10, just so you can kind of see yourself. So we're not taking any breaks for Thanksgiving since we have Wednesday lab. So if you plan to travel on Wednesday and you're a Wednesday lab person, just plan ahead is all I ask for that. And then, of course, the rest of it will be homework, which, again, I'll hand to you, and then quizzes, which we'll do on Wednesdays. So pretty easy. Like I said, you don't have to be digging around in Blackboard if you don't want to. And so we do have on there, so this is just kind of nice for lab, maybe, if you want to look at it. So it just has, like, some general safety things and pictures, and so you can look at that at your leisure. I have a few chapters uploaded, and so we'll talk about the textbook in a second. And so for lecture notes, I don't know if anybody poked in here. So I post my lecture notes, and so I do 2 versions. You can see the behind the scenes. I don't have a student mode on. There we go. Oh, geez, really? You made me refresh. Okay, but you have your lecture notes. So I provide both the PDF and the OneNote. I don't know if anybody tried to open the OneNote. So the only caveat with the OneNote is that you have to have the full desktop version of OneNote. So if you go into the apps, you know what I'm talking about, how you have those apps. So the app won't open it, but a full version of OneNote will. So I technically use OneNote 2016 if you're trying to download it and do it yourself. And that seems to work for reading the OneNote package files that I do. Because in those package files, I have these entire notes. And again, they're also available in the PDF form. So very accessible. And then at the end of the week, I usually upload and post my notes with all the scribbles that I drew on them. And you can always yell at me over email if I forget to post them, which I might. All right, what else? So textbook. So there's a couple of options for the textbook. So I think the official book on Ambassador is a custom print book. That's only part of the full. So the official textbook, so this is an old edition. So it's by Janice Smith, right? This general organic biological chemistry. And so I have it pulled up on Amazon. So I generally just tell people if you want to buy the book, buy whatever edition is cheapest. You have to poke around. I think people have been buying the 5th edition, but again, it's just whatever you find. I'm not attached to any edition, right? I'm never going to reference the textbook. It's just there for your reference. And so I say to students, if you're going to take the whole series of the Chem 104, 105, 106, I recommend buying this book then. Or, not this book, but, right, just the full textbook as opposed to what Ambassador says. But if you're only here for the Chem 104 class, I have another alternative for y'all. And so if you go to openstacks.org, you can find under science, so this is the chemistry, and it's called the 2E, Adams First edition. And so it doesn't match perfectly, but right, it's just a good Gen Chem textbook. So if you just want a textbook for reference that's free, this would be an excellent choice for this class. Totally appropriate, has everything you need in there. Like I said, it's not going to match, but the information is all there. So those are some options. All right, any other things we should talk about for first day? Textbooks. We understand the syllabus and how the course is going to run. No questions? All right, so let's start talking about, well, what is chemistry? And so I wanted to survey the class. So I'm going to hand out stuff, but what majors are you guys, or what are your career interests? Why are you here? Why chemistry? don't all answer at once. What is chemistry? What is it used for? How is it relatable to your life? Other than you probably want a passing grade. So any ideas, or what are our majors? What are our interests? You don't have to like chemistry or science either. Any thoughts? Yeah.
Well, I want to go into dental hygiene, so chemistry is like a prereq to get into OIT, so.
Excellent. So filling out prereqs, but right, we can talk about the chemistry of teeth too, going from like fluoride or hydroxyapatite, right? Looking at all those different chemicals, how does fluorine or fluoride actually work? Yeah. Excellent. Yeah, so then you can learn about some isotopes too that are going to be used in medical imaging, so some relevance to chemistry.
I mean, I'm just here for the science part of it, but I want to be a psychiatrist, so I mean, kind of need to know more.
Yeah, that's every chemist's favorite topic is drugs now. You'll find that we always talk about drugs in here accidentally. No. Yeah, excellent. I love it. So I need to start writing. So yeah, we got some medicine, biology. So I'll put, right, so many connections to chemistry. So imaging, meds, dental. What else do we have in here? What other interests, or why is chemistry important? Kind of both those things. Any other? What about that far side of the room over there? What are our majors?
I'm going to school for accounting.
Counting.
I don't know what connection there is.
Math is always good. I mean, chemists need accountants. Everybody needs accountants. And I'm sure you can find some chemistry related topics. And if you wanted to think about, right, the silicone and everything that went into your chips to make your computer, or even the ink that prints out, manufacturing, right, getting things streamlined, so all those could maybe go into counting. What else do we have? Yeah.
My angle is aerospace engineering.
Nice. Where's engineering? So a lot of materials would go into it, so you probably want some chemistry fundamentals, some corrosion things, all those good stuff. Definitely need more engineers too. Other majors, topics? Business. I'll put law. If you totally want to go into like science law, that's where the money is like patent law, working for that. So yeah, being able to merge the two of science and law is pretty powerful. Or understanding even regulations, right? For running a business, you have to deal with OSHA. What do you do with your waste? Yada, yada, yada. So there's so much connections there. Other thoughts, connections, majors? What about y'all in the back corner?
I'm also looking into medical imaging.
So more medical imaging. So a lot of, or how many people are here for like something for medical related? So a lot of people, you like future nurses too, maybe, or a lot of imaging, or so units are always important. And so we can also talk about just what is chemistry. And so obviously I'm biased, right? I'm a chemist. I study that, so of course I believe chemistry is very important. But we have it here in this little web, and it's kind of what I would say, right, our central science in a lot of ways, like building upon the foundations of what we learn here. We can, extrapolate to anything. So, right, you guys were mentioning imaging, so of course, right, you have to pick appropriate isotopes and like learning about that. Toxicology, right, would also be interesting, so poisons, detections. So of course, food science and agriculture. So ag, I'm gonna put a lot of money there. So big ag has a lot of money, and so we'll probably talk about this a lot, especially if we're talking about, so I'm probably going to talk about the Haber-Bosch process a lot in here, just because this is really relevant. So this is what they do on the industrial scale to make a bunch of ammonia. So of course ammonia is essential for fertilizer, and so if you have, right, if you've ever consumed nitrogen, like 50% of the nitrogen we consume just comes from this one factory where they make a ton of ammonia. And there's a lot of energy too that's involved in this process. It's very interesting and of industrial relevance, but that's again a big thing with ag is fertilizer or pesticides and all that stuff. And so of course we also have, right, geology. So if you have a chance to take a geology course here, I would. So tons of fun. So of course, right, that's just seeing our atoms and molecules now making different structures and how little impurities can influence, right, the CHEM colors, all those things are related. So chemistry, right, we could also talk about nuclear chemistry, so energy, so hopefully this will be a hot area of research. And of course, right, we have physics over here as our cousin, but we don't talk about physics. No. Nobody likes physics, JK, love physics. And so a lot of this chemical physics and math, right, we can go into like computational chemistry, which is pretty powerful, or any sort of modeling. So of course they use a lot of modeling now for everything really. So trying to do drug development or figure out different antibodies, what to produce, all of that, right, is computational chemistry. And we mentioned our materials, so engineering. So again, go into engineering if you can. And so the other caveat before we kind of dive into things is I've come to realize like math scares people. And right, so there's math and chemistry, so I've learned that's like why usually people don't take chemistry as their science elective, is I guess it's scary and math is scary. But right, we're here to learn. So I don't know what level of math people are at. So you have to have what, like math 65, I think, to be in this class. Somebody help me out. Oh, no, don't know. Anyways, it doesn't matter, right? My point is, it's fine. Hang with me, right? Get help, ask questions. We're doing this together. And my intention, right, is to not fail people, especially in an intro, right, Chem 104 class. So we're here to learn, so try not to stress out, just communicate, get help, because that's really the only way you're going to fail this class is if you don't do, like, large portions of lab or something, right? Or you were to put, like, 0 effort on a test, which I've never seen happen. So just, give your best effort, get help, don't be scared of the math. Like, we're in this together. All right, so let's kind of dive into things. Oh, so I did hand out your periodic table. And so I would keep this close with you. At night you can snuggle with it. But this is kind of your cheat sheet. So I think I'll continue this, at least in this class for sure. So I tend to give open note exams, so you can use the whole textbook and everything. But I would recommend that you kind of write your essential information on this periodic table. And then we'll kind of go through the periodic table, take a tour of it. And so, right, you're free to write on this. And then if you ever want another copy on cardstock, I have extras. But this is really kind of like your vital cheat sheet here. So I'd have anything essential here. You can, of course, write on the back. And this is yours to love and cherish. All right, so let's dive in. So chemistry is just defined as the study of matter. So of course, matter is anything that has mass and takes up space. So we have our desk here, right? The air that we're breathing is matter and takes up space. And so of course, chemists are really interested in changing them. And so matter can change from one form to the other. And so of course, chemists are mainly focused on chemical changes, such as in a chemical reaction. And so usually there's some sort of rearrangement of atoms. Again, we'll see that as we dive in. And of course, you're probably familiar with like combustion reactions, so either burning your gas stove or when you start up your car, assuming it's gasoline powered, right? All that combustion gets it going. And so we'll also look at the differences between chemical and physical changes. So in physical changes, we'll talk about how it just changes state. And so notice, right, it doesn't lose its identity, so there's no rearrangement of atoms. So it's just going from solid to liquid to gas. And of course, we have water as the example. So most people have seen water in all three states of matter, right? Steam, liquid that probably all are drinking, and ice that is in your freezer. And again, feel free to stop me, slow me down, ask questions. I tend to talk fast, but that's also because we have a lot of stuff to cover. And so now we can at least start with our states of matter, so classification of matter. And so matter can be classified according to its state. So we'll mainly just be focusing on the three main ones, right? Solid, liquid, gas. People always ask about plasma, but that's not our main focus, and we don't really see plasma normally. And so you may see some abbreviations as we go through the quarter. So solid, if you're looking at in a reaction, will be designated with an S, and an L stands for liquid, and a little g stands for gas. And I'll put over here, this will be kind of for later, but AQ, if you see that, that just means an aqueous solution. And so then we would also write, like let's say we're trying to write a balanced equation showing what reaction we're doing. So we'd indicate what our reagents are and then what state they are. And so that's what it means, right, by like composition. So, I could write H2O as a liquid, so that's telling you, right, we're adding water in a liquid state. Or, right, if you see it differently, so H2O gas, and sometimes you see the gas form a lot, especially in these kind of like standard reactions. And so that just means in the gas form. And so now let's look at the atomic level, what this means. So in our solid matter, right, our particles are tightly packed and fixed in place. And I like to say, right, fixed volume and shape. That's another way to say that. But we're looking at the solid, right? So we have to remember there's still motion, right? So they're still vibrating, those individual atoms, right? They still have their electrons circling around. So there's still movement, right? So we can't say that there's no movement. But there's not so much movement, right, where they can slide past one another like the liquid. So in the solid, they're going to have some vibrational motion to them, but they're not sliding past. And so as we move from solid to liquid, so we're going to be adding energy then. And so with that energy, now these particles can kind of move faster, right? And then they start to slide past one another. And so we can say, right, fixed volume and no shape, or no fixed shape. And you all have seen that. So you've taken water, right? You can pour it from one container to the next. So the volume remains the same, right? But it just takes the form of that container. And again, they're just able to slide past. And so again, they're still relatively closely packed, but just moving around so that they don't have a definite shape. And then of course, if we add even more energy, then we can go from liquid to gas. And now in the gaseous phase, right, they're really spread apart. So they're all moving around wildly. And we can say that we have no fixed volume or shape. And then what else could we say? Well, I'll just say it. So gases, so the special thing that they have is that they are compressible. And so that's different from liquid and solid, right? Liquid and solid, you can't pressurize them and make them take less space, right? But gases, so have you all seen like big gases, like the nitrogen tanks that they fill up your tires with? Yeah, so, right, you can take that nitrogen, compress it all the way down to even a liquid form, and then you open up that nozzle in the tank and it's coming out, right, as air at the appropriate PSI based upon your regulator. So gases are compressible. All right, and these are just the words that accompany the picture, so we kind of covered that. So again, just hitting the highlights. So we said solids, they're packed and fixed. And again, they're going to vibrate, but they can't actually move past. And there's our fixed volume, fixed shape. So some examples, so of course, ice, aluminum, diamond, and you could go on and on and on listing a bunch of solids. And so again, liquids, there's a key fixed volume, not a fixed shape. So they all have that flow ability. And again, you could go on and on. So water, different alcohols, both the ones you consume and of course the ones you don't, like isopropanol. And gasoline, so that's basically octane, so an organic chain. So all of those are liquids. And then gaseous, so there's our key term with compressible. And again, the nice picture, so showing how solids are not compressible, so there's nowhere for those atoms to go, versus the gas, you can compress it, obviously down to a certain physical limit where the atom's size does matter. So. And so something else that we want to be able to do then is be able to classify matter. What is something? Is it an element, a compound, a mixture? And then what kind of mixture? And so let's kind of go through this. And so the first thing you're going to do is kind of figure out, well, you know, is it one type of particle or not? And really, you have over here on this side, right, you're trying to determine, is it an element or compound? And then go from there. Or is it a mixture then of two or more elements, compounds? So we'll go through this. And so, right, you have some places to start. So let's start with, well, what are elements? So those are kind of simple enough. So anything, right, on this periodic table is an element. So that's a good place to start. So if you don't know what something is, right, look for it on the periodic table, like gold, nickel, iron. So all those, right, so those would be pure elements. And so that's the distinction here. So once we have these pure substances, then you're just defining element versus compound. And then does anybody know what makes a compound? Definition for that? Any guesses? Or maybe even what is a compound? Can you name a compound? What was the compound? I know the lab people have an advantage. H2O. So let's look. So you got what I would say half our definition. So it's two or more atoms, and this is a good distinction. So we'll kind of look at some caveats here. But then what else does it mean? So we have two or more atoms, but there's a little something else to it. And you said H2O, but what does that mean? And like, so it's a pure substance, right? So then we can say, I would call it defined chemical formula. So water, right, is always H2O, right? So you're never going to have waters like H2O2, right? That's now a new compound. That's hydrogen peroxide. So we'll add that. So defined chemical formula. And I think you're starting to see that trend. So we saw H2O. We can add, right, like NaCl, so sodium chloride. This is where I already go into drugs, the class. So, for example, we can look at, oh, come on, that's not what I want to look at. So aspirin, for example, right? Aspirin itself is a defined compound, but then, and now I'm totally blanking on which medicines have like combinations of different compounds, right? But that would be a mixture. So what is it? I think it's Alka-Seltzer, cold. That has a bunch of crap in it. Of course, trying to get anyone to tell you what the chemical composition of anything is. So some of these Alka-Seltzers, they have both aspirin and then, now I can't remember what makes them fizzy. Do they not have packaging? Oh, there we go. Oh, I can't read that. Okay, I'll look at it later. Oh, here's another one. So drug the class, right? THC. So that's going to be defined chemical formula, right? While all the other things, so right in a DAB, let's just say there's concentrates, there's terpenes, right? So those are all different chemicals, right? Each terpene is a different formula. So we could look up limonene. So that's going to be a terpene that's commonly found. So that's the distinction. You have to have a defined chemical formula, but then everything else is mixtures. All right, so now drug the class already. So I'll put, right, THC as a defined chemical formula, or terpene. So terpenes all smell nice, so that's like your limonene, like the wintergreen smell, pinene, all those are terpenoids. And so then under mixtures, so I'll put this under homogeneous, and unfortunately, so I don't know, so I'll call it DAB, right? But that's just the mixture of all the different chemicals. So that's going to be the mixture of the THC, the terpene, all that weird gooey stuff, right? And you can kind of tell that that's something impure, right? Because the DAB always looks weird. It's like kind of yellowish. Whereas if you get it pure and pure, and get out the pure THC, right, that's going to be a white chemical. And that goes back to what I said in lab, and what you'll hear me say is organic chemistry is just a bunch of, right, white liquids, white powders, everything looks the same. So you got to label stuff. And so again, I'll put under there aspirin versus our Alka-Seltzer, which is more age appropriate for your class, but unfortunately I couldn't find all the chemicals, because why would anyone want to know what chemicals are in their medications? All right, so let's go back to element, because we need to make a few distinctions. So we said, okay, well, everything on the periodic table is an element, but let's look at a few tricky things. So here's my periodic table. And so something that we want to define is what I call our diatomics. And so diatomics are just certain elements that are found as a pair. So all that means that in their elemental form, they can't exist. So for example, let's start with hydrogen. So lone hydrogen by itself, just H, that doesn't happen. So in its elemental form, so how it's found as a pure element, it's a diatomic, meaning that it's bound with itself. And so there are 7 diatomics. So I would go ahead and grab your periodic table and highlight or draw around your 7 diatomics because it's going to crop up again. So hydrogen is the little loner out there, and then the other 6 make this little pattern. It looks like a 7. So that's nitrogen, oxygen, and then fluorine, chlorine, bromine, and iodine. So just label those, denote those. So when you see them written out again in their elemental form, it's always going to be 2 of them. So H2, N2, O2, F2, Cl2, Br2, and I2. So all these, again, they're still considered elements. And so, right, that's not 2 different elements. So someone gave the definition that it's 2 or more atoms, right? So it's 2 or more different atoms. So just make that distinction. And so there are other tricky ones. So let's pull up. So phosphorus. And so Wikipedia is not really a good source for like current events and like history or anything, but it's actually pretty good for science, so that's why I pull it up a lot. And so phosphorus is one of those. So we can already see, well, there's different forms. And so there's a thing called, so it's called an allotrope. And let me make, so allotropes are just defined as different geometrical arrangements of the same atom. And we'll look at some. And so we were starting with phosphorus. And if we're not talking about drugs in here, we're talking about warfare and explosions. just so you're ready for the class. And so, of course, right, people are usually familiar with white phosphorus from war. So this is white phosphorus that was used, and it's in this, again, structure. So you can just appreciate the physical structure. And so this would be P4. And so notice it's called P4 too. So that's the other thing. So it's still an element, right? It's just showing you it's a different form. That's why they call it P4. And then there are other forms of phosphorus. So there's also red phosphorus. And again, just appreciate the difference in structure. That's what gives it the difference in reactivity. So this is formed from the white phosphorus, and then you have a different geometrical arrangement. And so you can see, right, there's also violet phosphorus, so different structures, and black phosphorus. So you don't need to know, right, all these different things. Just know that there are different allotropes of phosphorus, so you may see that. And so you might see phosphorus written as like that. Again, still an element. And so another one that comes up is sulfur. So sulfur, sometimes it's written as S8. So that's still its elemental form. And so let's look at sulfur. And so sulfur as an element makes this weird 8-membered ring thing. So that's why sometimes people write S8. And so sulfur is nice and yellow. Where is the solid state structure here? So here's the S8. So it does this weird ring thing. And again, just appreciate it, know that you will see it. And then the last element that we'll focus on with a lot of allotropes is carbon. So does anybody know some allotropes of carbon? You probably do, and you may not realize it. So what are some allotropes of carbon? So that would be a compound, right? So we'll put that under the compound category though. So CO2, so that does contain carbon. That's our defined chemical formula. So what else might carbon be? So just something that's pure carbon. You know, so I don't think carbon fibers are part of it. I think I have to look up exactly what is a carbon fiber. I don't think that would be an allotrope. Other guesses? Other guesses? Some of the ladies may be wearing carbon allotropes. Any guesses? Diamonds, yeah. So diamond is an allotrope. So let's look at our wonderful, let's look at our allotropes of carbon. And so diamond has this tetrahedral structure, again, all repeating carbons, so that gives it its strength. And so now we've given away another allotrope. So these are probably the two you all would be most familiar with. So what's graphite? Yeah, so that's just your pencil. And so you can see right away from the structure kind of the difference between graphite and diamond and why you can write with graphite, but you can't write with a diamond. And so it's all in this little structure right here. So graphite forms all these sheets, and then they're bound just by these intermolecular forces here. So this is fairly weak. So it can shear off, right, in sheets, and that's how you can write with it super easily, while the diamond tetrahedral form is a lot stronger. Although technically I think graphite's the thermodynamic sink, so if you gave your ring enough time, it would eventually become graphite, but not on your lifetime scale. And so these are a bunch of other allotropes of carbon, but really I want to point out, so this one, D, so this is the buckyball, or C60. So it looks just like a soccer ball in its geometry, but this was like a huge deal when this buckyball was created. So this was done at Rice University, and then this kind of led from these buckyballs to these carbon nanotubes, which are being used for a whole bunch of different applications now, and they can grow these carbon nanotubes. And so there's other variations here, but again, we don't need to know all of them. So diamond, graphite, and I'll put on there the C60 buckyball. It's a very important moment in science. All right, so let's go back. So we looked at our elements, so we went over diatomics and allotropes. So don't forget all those. And so I feel like we've gotten a handle on our compounds. So again, compounds, you just have to be careful that you're looking at one compound individually. Again, you know, you can look at your medicine when you get home, like what's it made with. Sometimes they're also put like filler in there, right, that's inert. So that's all the distinction, right, between a chemical versus a mixture. And so now let's look more at our mixtures. So we said mixtures have two or more elements or compounds. And then once we determine that, we just have to determine, is it heterogeneous or homogeneous? And so it has this thing, uniform throughout. So I'm always thinking, right, is the first bite the same as the last bite? Because we also talk about food a lot in chemistry. But I'll say, like, for a heterogeneous mixture, I would put under there, like, a Java chip frappuccino or something. Right? So you can have your first sip, maybe that one had a huge chunk of chocolate in there, but then by the time you get to the end, right, it's mainly just coffee. So that's going to be heterogeneous, right? Different things throughout. Or another example, so they have the wet sand. So you want to think about that, like if you were to just scoop some sand and water from the ocean, you would have your top layer is probably mainly water and then some turbidity and particles floating around, and then the bottom is going to have, right, more sediment. So it's not uniform. So versus something homogeneous, so they have tea. So of course that would be, right, your sugar and water, and then all the tannins that go into flavoring your tea. So a bunch of different chemicals in there. I'd also, you could go crazy with drinks. So Gatorade, Coke. Coke as in Coca-Cola, not cocaine, obviously. Cocaine's a defined chemical formula. Just want to be clear. Again, drug the class. Drink. Let's think of some more, what are other heterogeneous examples of a mixture? What do we think? It can be anything. It doesn't have to be food related. It can be anything related.
Tires, technically, right?
Huh.
Tires with tread pattern and how they wear.
I would more think about like the rubber itself, but then that's probably like a polymer. So that's kind of, I guess that's kind of like an awkward one. What about like, let's see, you could do Swiss cheese. So that, right, it's got holes, so that's not very homogeneous. People usually say like salad dressing, right? That's always like the easiest, heterogeneous. Bread would probably, I would put bread under there, although you could have some arguments. So I would say especially wheat, right? Because that wheat has like more grains and weird stuff versus like a total white bread. That's more homogeneous. But so there's some room for argument. So on an exam, I try to be straightforward with the examples that I choose, but you can always write explanations to me in the margins of what you were thinking, so I can follow your logic. Other heterogeneous examples? Dirt would be a good one. And so dirt you could almost put under either one, so it depends on your dirt. So we could say, so probably most dirt is going to be more like heterogeneous, and it depends again on your sample, right? What if it has bugs or different size of rocks? But then if you were to have, right, like let's just say really beautiful like white sand, then that might be more homogeneous. So, again, there's judgment calls. So it depends, like, is that sand up here all perfectly uniform, relatively same size and size, then you probably say it's homogeneous versus like the dirt, if it has bugs and rocks and different sizes, yeah.
Would soda be considered heterogeneous because it has bubbles?
I guess I would put it under more homogeneous though, because the bubbles are like more uniform throughout, but I kind of see what you're saying. Yeah, I'd put it under the homogeneous category, since it's all pressurized at the same atmosphere for your Coke can. Other thoughts, examples?
What about water with salinity levels? Would that be something that would apply to it as well? Because then you could do it at different levels as it's not as consistent all throughout the ocean. have the water that brings in, or fresh water that brings in different minerals into the water, and then out deeper, like towards ice caps, it's absorbing more of the salinity out of it, so they're not as salty.
Yeah, so that would go more again with like the sample. What is it? Is it like, because usually even if you're getting a sample, because you're correct, like it's not going to have the same salinity, but then like your sample itself should be homogeneous, maybe, because then it's like, well, if it's real world data, you know, did you scoop it up right next to an iceberg that was really dirty and you got a bunch of rocks in there? So that's always like, you're always looking at the sample. So there is ambiguity, but yeah, I would mainly put like seawater under homogeneous, but yeah, but you are totally correct that like the ocean is not perfectly homogeneous in salinity. I think it's roughly, gosh, it's like 3.5% salinity or something. All right. Any other questions, comments about sorting, classifying? All right, so this is just kind of the text that goes with it, so I'll kind of just skip that, but you have that for your reference. And so I always joke that, right, chemistry is a lot of the time you're adding solvents and then removing solvents and just trying to separate things, so that's really chemistry. I also had a professor once say, my 3-year-old can mix any chemicals together, but it's all about, right, the separation, the purification. So that's really what makes the chemist, right? Again, anyone can mix anything together, but can you separate it? Can you analyze it? Can you get something pure? And so one common technique for separation is a distillation, and so this is just provided as an example here. I want to point out the extreme hazard in the open flame when performing a distillation. So I don't know why the textbook has it like this. You would absolutely never do a distillation with an open flame. That is a great way to start a fire. And so now there are heating mantles that are nice and safe, at least as long as you don't forget the thermocouple, otherwise they heat uncontrollably. But yeah, you would use a heating mantle, but basically source of heat. And so you can either separate two different liquids if they have a large enough boiling point, or you can separate, right, liquids from solids, such as if you were stranded on a desert island, you could make yourself a little apparatus, right, to evaporate water and then catch it. So usually like a cup within a cup type scenario. And so all this does is it boils some liquid, and then it reaches the top here, so our condenser. And so notice we have water going through this, so the water will help cool the vapors back down, so then they'll condense down into here, and you'll collect your pure, happy sample, or at least hopefully pure. There's one technique. And you'll look at other techniques in lab, like just physical separations and all sorts. All right, so chapter 1, I admit, is not the most fun because you have to talk about units and conversions because we have to set ourselves up properly. But let's look at, well, why do units matter? And so this is a pretty great story. And so we have that this Boeing Delta was supposed to launch off and visit Mars. And so the problem started here. So it says the software calculated the force that the thruster needed to exert in pounds. But then the next piece of code was in newtons per square meter. So whoops. And so the engineers at Lockheed Martin were using force in pounds. But they should have apparently converted to metric units. And so the engineers at NASA assumed that they were in metric units. And then what happened as this little craft entered the atmosphere too close and probably burned up. And so there went who knows how many millions of dollars. So units matter. So right, make sure you always write down your units in your labs. So Also units, if you have to take physics, so I'm not the biggest fan of physics, but you can totally get through physics with unit conversion. So if you don't understand anything, just unit matching, and that's a great way. And chemistry too. And so let's also talk about, see if we can play a guessing game. But you'll notice, right, science looks at things from like teeny tiny to really large. And so let's kind of think about what scale all these are on. So what's a human hair? What kind of scale? Like meters, millimeters, micrometers? Any guesses? No one wants to venture a guess? You don't have to be right. What do we think? We think it's in millimeters. We think it's smaller, micro, nano. So micro, so that would be correct. So it's about the order of micrometers. So that's 1 times 10 to the negative 6 meters. So just kind of getting us oriented. What about the size of an atom now? And does anybody know the special unit that chemists use? So chemists usually bring up the size of things in angstroms, which is this funny little symbol. So this is 1 times 10 to the negative 10 meters. So getting pretty tiny. What about an elephant? So how big is an elephant? What does an elephant weigh? A lot. So what's a lot?
Meters, kilograms, feet, pounds.
Yeah, so I'm looking for either kilograms or tons or... So what do we think? Once you know that how big it is too, I'll take meters if you have meters guess. Take any guesses. So I think they're a little fatter. So I think they might be more like 2,000 kilograms or a couple of tons. So some of them I think are like up to 15,000 pounds, so pretty large, so pretty fat. And then what about distance to the nearest star? Yeah, you can give it to me in light years.
Oh, I don't know the answer. I just know numbers.
Oh, so light years. So let's at least do light years. So light years.
Astronomical units.
So astronomical units, so super, super large. And now I have to look at the conversion. There we go. Anybody know the distance in light years to the nearest star? By any chance? What did you say? Yeah, the next closest one. So it's Alpha Centauri. So this little star. And so it's about 4.35 light years away. And so I have the conversion. So that's 4.12 roughly times 10 to the 13th kilometers. So fairly large. Yeah, really far. And so, right, you're already getting a sense of it. So we're working with teeny tiny numbers. So we might see small numbers in chemistry, but if you wanted to, do physics, astronomy, so now you're suddenly talking about light years, kilometers. And so that's why we have our metric system. And so our metric system is, of course, easier compared to our American system, at least it's supposed to be, since everything is based on multiples of 10. And so we notice that we have our base units. And so we'll go through these. So eventually we'll talk about moles, just not today, but this is a special unit for chemistry. Let me add a chemistry unit. So this is only in chemistry that you would see that. And then so length, your standard unit is in meters, that's your base unit. So your mass, your base unit is in grams. Volume, it's in liters. And so temperature, you probably wouldn't be doing conversions, but tend to be in Celsius, but I'm going to put Kelvin there because this is really important, especially when we're talking about thermodynamically relevant values. And then we also have seconds or bytes, but we don't usually do bytes. So mainly it's meters, grams, and liters. That's our focus. And so we have multiples of 10 are created by adding a prefix to each base unit. And so we have, so let's look at a couple of things. So we want to be able to write what's called these conversion factors. So I'm going to go ahead and pass out kind of our little practice for this. So we can go do this. Oh, okay, I already got you. All right, so let's kind of look at this. So before we get too lost and confused, so notice that a conversion factor, this just expresses a relationship. And so let's put it in something that we know, right? So 12 inches equals a foot, or we can write it again the other way. 1 foot is 12 inches. And so why we're doing this is eventually we're going to use this conversion factor, right, to get to the answer we want using dimensional analysis. So all our conversion factor is a relationship, right? So I'm trying to go slow so I don't lose people, because sometimes I lose people on these conversion factors. And so if we go to the next page, I think this is clearer. So if we go here, so this is confusing to me. So you have to pay attention to what they're saying here. So it says quantity in one base unit. So what it means is how many tera whatever, and I'll just say like teragrams, because that's easier for me to, if we talk about a unit, than rather just tera whatevers. So it's saying there's 1 over 10 to the negative 12s, right? Teragrams equals 1 gram. That to me is a little confusing how they say it. So I think this way is better. So if we look at this chart, I like the way this one's written out because the multiplier, right, this is by the base. And so that means right by our base unit, so what it's saying is we have 1 times 10 to the 12 grams equals 1 teragram. And we can write that as our conversion factor. Grams in 1 teragram, or, and again, we're just writing it both forms, just depending on which way we're going. Now you could use the negative exponents like they do here, but to me it's more confusing. So I would just stick to the positive, and I can write the negative though. So what we're saying, and it's all the same thing, is 1 times 10 to the negative 12 teragrams, right, equals 1 gram. So, right, same information, but what I find is most people get confused using these negative exponents. So it doesn't matter which conversion factor you use, but I would encourage you to use positive ones, just so you don't have to be worrying about the negative and keeping track of it. And so let's look at another example. So they did the millimeter ones for you. So again, you can look at, this is by the base unit. So now it's a lot smaller, right? And so this is, again, where people could get confused. So now we're saying that there's 1,000 millimeters in 1 meter. Or if we do it by the base unit, and what they have here, right, 1 times 10 to the negative 3 grams equals 1, right, milligram. So that's the negative. And so notice, right, you can multiply this by 1,000, right? So by 1, essentially, so 1,000 over 1,000 gives you back, right, to these same positive ones. Everyone follow with that? So I'll write them both out, so 1 milligram. And so we can do, let's just do nano together. So this would mean like 1 times 10 to the 9th nanometers is equal to 1 meter. Or again, 1 meter is equal to 1 times 10 to the 9th nanometers. We do the negative 1 times 10 to the negative 9 meters equals 1 nanometer. And again, you can write that relationship the other way. It doesn't matter. All right, so take a couple of minutes now. So fill out the rest of the chart with your neighbor. So kind of walk through it. Just what does it mean? You have the multiplier. I'll kind of come around and see how we're doing. I know we're slowly running out of time. And yeah, you can hop over the aisle. Don't be shy. You can talk. You guys are kind of quiet. But yeah, take some time. I'll come around. If you're far away, scooch in. Don't be shy. Change numbers. Oh, so I just picked grams as like our base unit. So like I was saying, so we could call it meters. So like 1 times 10 is 12 meters, and it's equal to 1 terameter. So yeah, make sure that that's teras.
The numbers is not what's good.
And yeah, because a teragram is a big T. Yeah. There's no little t, but there are big M's and little M's. Yeah, teras is a really weird unit. Yeah, so then you can try the same thing for giga, right? So giga, it's 1 times 10 to the 9, so it's by the base. So we could pick 1 times 10 to the 9 meters or seconds or liters, whatever. So one of those will equal 1 gigameter. Giga, whatever you pick. Yep.
But
And then of course, right the other way. And then I would really focus on the positive exponents that make you comfortable. You're more than welcome to write them in the negative way. Again, I think students start to get confused if they have like 4 options to choose. positive thoughts.
I feel like
Yeah. Yeah. But if, for your sanity, if you just wanna write all the positives and whatever makes sense to you, do that and focus on it. Micro, it's a mu, is what it's called, but yes, like a U with a Q. Yeah,
it's very bad science for everything. What's the? I'm a mountain science.
So this is where it gets weird, because it's 5 of base, so this should be a negative there. Or you could turn it into the positive way, where it's 1 times 10. Yes. So yeah, you could also turn it into the positive by 1 times 10 to the 6 micrograms is equal to 1 gram. So, it's whatever you want to take. I usually take the meters or grams.
So it doesn't matter.
Yeah, so for the negative, you want to use a big M.
Oh, okay.
Yeah,
Oh,
and
it
then-
shows.
yeah, milli, a little M, and then micro, is that your thing? What? Yeah, just let me know what. Yeah, and then make sure you put a big T, although it doesn't matter too much for the tera, because it's not an E's, but like that mega. Yeah, there's multiple M's, so it gets confusing. So you have to use a big M for mega, small M for milli. Yeah, so that would be a little M at the top and bottom. And so I would do like, if you're doing like mega, you're doing like big M and then a little M.
No, I guess it's not because it's not.
And then millimeter, right, it's just cute little M's. Okay, yeah, you may want to add just like a base unit. You know, it's almost as people like math or How are we doing?
Are you supposed to like swap like means and measurements like error sheet so that just stick
Yeah, it's up to you, yeah. I usually either pick like meters or grams all the time, or,
Are we gonna go over the answers?
yeah, at least like spot them.
Or all of them, maybe?
Yeah, we could do all of them. Okay, are we?
I got the I'm a numbers girl. I got the numbers right now.
Yeah, so make sure you put little labels so we know.
That's where I'm lost.
These two, well, if these two are right then.
Yep, so that looks good, but then we need to figure out, yeah, we have
He also
5
said
in
that
here.
it doesn't matter, so.
Right, they can.
Yeah, but we have to write some labels.
Yeah. Okay, so then I do know how to do it. Okay, then I'll do it.
Oh, gotcha.
So. Okay, so that needs to be like this.
Well, it's like grams is the multiplier, if you use that. Compare. right, let's try to go over them all. So I'll start with the top here. And I'll probably mainly stick to positive ones for my sanity. So 1 times 10 to the 9th, and I just am going to pick grams. So grams is equal to 1 gigagram. And so make sure you use the appropriate symbols. So with giga, it's a big G. And again, I'll just rewrite it to show it's the same relationship. I'll refrain from doing the negative one right now, unless anyone wants to see it. And again, you can always talk to me individually as well if you want to use negative ones. But I will write what I think is the most clear way to do it. So again, just multiplying by the base. Make sure you use a big M for mega. And then kilo. So 1 times 10 to the 3rd grams is 1 kilogram. Again, just writing that relationship flipped. And so deci. And so deci is where we have, right now we have a negative by the base. So we could do 1 times 10 to the negative 1 grams, right, is equal to 1 decigram. That's what it's saying. No, I put decimeter for some reason. Or, again, if we don't like the negative exponents, so multiply everything by 10. So now we have, so 10 decigrams is equal to 1 gram then. And then, of course, you can flip that. And so same thing. So now I'm going to write these a little differently. So now we're saying, well, we have 100 centimeters, right, in our base unit of meters. And we could have written that, right, 1 times 10 to the negative 2 meters is 1 centimeter. Then multiply by 100 on top and on bottom to give you this conversion factor, the positive one. And so milli was done. So notice milli is little m. And then I had a few questions about this micro. So this is a mu symbol. So it's like a U with a tail in the front. And so now that's 1 times 10 to the 6 micrometers is equal to 1 meter. Again, you could have done it by the base. I'm just doing the positive one. So that's negative 6 meters is 1 micrometer. But I like this form better. So nano. And then so pico. So 1 times 10 to the 12 picometers is equal to 1 meter. And of course you can flip that. And then femto. So you probably won't see femto, but well, recently he has passed away. So Ahmed Zewaili was the one who won the Nobel Prize in chemistry for his research on femto laser spectroscopy. And he was also a really important political figure in Egypt, but he died. And so femtometer is 1 meter. Yeah, I will post these notes later. I don't know, can you see that? Yeah, I will probably have to post these notes. What if I do 2 pictures? So, can you read that?
My eyesight is not the most reliable.
Is that better?
That's good.
And then I can scroll up a few times. So I'll try to, again, I'll post these notes on Wednesday. So on Wednesday, for sure. Again, you can yell at me. Oh, I think we almost. All right, so now let's look at kind of, well, where are we going with this? And so now we want to be able to convert. Actually, let's do a practice before we do all that. So let's just start. So let's convert 6.12 times 10 to the 12. Let's do picometers to meters. We'll start off relatively simple. But let's go through this together. So how would we set this up? Why do we bother writing all this? And so we want to set up our dimensional analysis. And so we want to start with what we know. So 6.12 times 10 to the 12 picometers. Then we'll have to pick, right, our conversion factor. So I'll just leave this blank for now. And then we're looking at, so in this case, this is a simple conversion, and we're just going to meters. So that's one of our base units. So we could put meters there. And so now we want to pick, right, the correct conversion factor. And you can even kind of set yourself up for success. Well, I need meters on top, so that means I'm probably going to want meters on top for my conversion factor. And then if picometers, right, needs to cancel out, that means I'm going to need picometers on bottom. And so now you can look at your chart. Oops, I scrolled too much. And so you kind of have two options here, right, written one way versus written the other way. And so I'm going to pick this second one because it has the meters on top, the picometers on bottom, so that's the appropriate one. So 1 meter, 1 times 10 to the 12 picometers. So again, just grabbing our conversion factor, our relationship. And this could be any conversion factor on an exam too. I might give you just like a random conversion factor. So you just have to be able to plug it in. And so of course you could do some mental math, right? We all remember that dividing is just the same thing as subtracting exponents. But of course you can also plug it into your calculator. So what do we get for our answer? So our answer. 6.12 Yep. So 6.12. And so we'll talk about sig figs probably on Wednesday at this rate. Although we still have 30 or 20 minutes. We'll see how far we get. But basically when we do our converting, we want to keep all our units here so our conversion factors do not count towards sig figs. And that's okay if that's a foreign word right now. Like I said, we're getting there. So let's try now a maybe slightly more difficult one. So I want to write, so 0.05 kilometers to centimeters. So any thoughts about how we could do this? So take a minute or two. So how would we do this?
I think you go from kilometers to meters and then go from meters to centimeters.
Excellent. So this is what I would call a two-step conversion. All right, and you can always, I call it, right, your safe space, right? Your meters, your base unit, that's always kind of your safe space. So then you want to think about, well, if I need to go, right, from kilometers to meters to centimeters, right, what conversion factors do I need? So I'll give people another minute or two to kind of get the answer and look at your conversion factors.
5,000 centimeters.
I think so, but I have to do the math. let's see. So let's set this up so we can walk through it together. So I just started right with what we know, and then y'all told me we wanted to go to kilometers to meters, and so we can look at our conversion factor. And so I'm doing this kind of explicitly right now, but then we'll pick right this one. So we want our base unit on top, kilo whatever on bottom to cancel. And then so we write that down, right, our first conversion factor. So again, just going kilometers to meters. So again, meters is going to be on top. So 1,000 meters is 1 kilometer. And then we need to go from meters to centimeters. So there's 100 centimeters. So the unit I want should be on top. One we're canceling goes on bottom. And so again, just cross your units out. So kilometers will divide, right? Meters will divide. And then we could do some either mental math or plug it in. So 0.05, and I'm just going to go ahead and multiply it. So we have 10 to the third times 10 to the second, so that's times 10, 1 times 10 to the fifth here. And so that gave us 5,000, like you'd said with your mental math. And you could have plugged it in explicitly. I shouldn't take so many shortcuts. So times 1,000 times 100. So any questions so far? Have we seen this before with like dimensional analysis and unit converting? So a few no's, so there's a mix in here. So if you're not used to this style, I would kind of encourage it just because unit converting will help you, and if you can line up your units, you can definitely double check your work. All right, let's try this practice. So let's see, let's start with, let's at least do the first 4. So I'll give people probably like 5 minutes, kind of work in your pairs and your groups, and then we'll go over these answers. So then you can just look at the conversion factor, and if you want, so instead of the K there, you want meters, right? So 1 times 10 to the third meter, and then kilometer. And then so you want to pick the conversion factor of kilometer on top. So you want this one.
So one,
1 times 10 to the third meters.
so would it be 5 times 10?
5 divided by. So right, so go back to this, so you're picking this conversion factor. So, right, we want to go from meters to kilometers, so at least it's the base unit. So then I would look at this one, and so we want kilometers, we want the conversion factor of kilometers on top. So then you pick this one, and then
So it
just
would be 5,
divide it by that, essentially, is what it's going to look like.
so like, it would be 5 kilometers divided by 1 times 10 to the third. I've never done this one.
Well, it's just, yeah, the words, because the problem is, right, you're starting with 5 meters, and then you're multiplying it by this conversion factor such that meters cancel
You can write
out.
on this.
Oh, it's just, I don't have a pen that writes. But,
You can use the other end of this.
fancy. But, yeah, if I just write it here, right, because you're starting with 5 meters over 1, but then you're just picking the conversion factor that gets rid of the meters. So meters there, and then 1 times 10, so you're literally just copying that. So then it looks like that, right? So it kind of looks like you're multiplying, but yeah, you're like dividing to cancel out the unit. But,
No.
I don't know. All right, we'll do some examples, but, all right, are we ready to go over these at least? So let's go through them again slowly. So we're all on the same page. So, right, we're trying to go from 5 meters to kilometers. And so, right, I'm just starting with what we know. So 5 meters over 1. So this is just like a mathematical formality, right? I'm trying not to scare people. And so now we want to go to kilometers. And so now we just want to pick, right, the appropriate conversion factor. So if we look, right, we have kilo and we have meters. And so if we want to go with kilometers on top, right, we want to pick this conversion factor. So it's just all units at this point, right? So we're picking, so we have 1 kilometer then is 1,000 meters, right? So do we understand? So this is just our conversion factor. And so we can tell it's appropriate, so meters cancels out, right? This leaves us with kilometers. And now at this point, we can just plug it into the calculator. So 5 divided by 1,000, so that gives you 0.005 kilometers. Did that help you?
A little bit, yeah. I just have to see it a couple times and then I'll get it.
So let's try the next one. Again, we'll walk through it slowly for everybody. So 3 grams, again, over 1, just a formality. And then, so what conversion factor did we pick? So, right, I'm just going to put CF for conversion factor. This equals, right, we want milligrams. So how do we get from grams to milligrams, right? So look at your chart. Where's the milli? Where's the grams? All right, I'm gonna go ahead and put milligrams on top, because that's what I want. I know I want grams to cancel. So now just what's the relationship then, right, between milligrams and grams? What does your conversion factor say?
1,000 over 10.
So perfect, 1,000 over 1. And so now we can just multiply across. And so what do we get for our answer? So 3,000. Everybody feeling okay? And don't be scared to say you're not. So we want to go slow in the beginning so that everyone's on the same page. And then again, as all our math skills pick up, then we can all go fast. And I apologize if anyone is bored. That's just the nature of the class. And we got to get everybody on the same page with converting. All right, what about 7 meters to centimeters? You could probably also do this one without a conversion, but we can also do it formally. So, right, centimeters over meters is my conversion factor. We want centimeters. We're trying to cancel out meters. So what numbers could I put here? What'd you say? Yeah, so there's 100 centimeters and 1 meter. There's our known relationship. And so what's our final answer? 700. And then the last one I said to do was this one, correct? And so this one, what was tricky? So you had to probably do a 2-step conversion. If you're more mathematically inclined, you may start to see kind of the direct relationship. And I can kind of write that out where it comes from, but then I'll show the 2-step. So, right, if you're a mental math person, you're thinking milligrams, so that's 1 times 10 to the negative third, right? Kilograms is 1 times 10 to the third. So they have a factor of 6 difference. If you, again, this is like, if you're there, it's fine. If you're not, don't worry about it. So this is what I would call our 1-step conversion factor. So you can see that factor of 6 difference between them. Or we can do the 2-step. Perfectly fine. I'm just trying to show different ways for people. So 60 milligrams over 1. So let's take it right, milligrams to grams to kilograms. Again, with grams kind of being our safe space. You always got to have safe spaces, especially with math. So I'll go from milligrams to grams first. So grams on top, milligrams on bottom. So 1 gram is 1,000 milligrams. And then from there, well, now I need to go from grams to kilograms. So put kilograms on top, grams on bottom. And so 1 kilogram is 1,000 grams. Oh, there it is, our factor of 6. If you didn't see it, now you see it. And I'll just plug it in so I don't say the wrong answer. So 6 times 10 to the negative 5th kilograms. So any questions so far? Oh, let me pass out. So, okay, a couple of things. So we're about done with lecture. So I withheld some information. Now, I really do this because I want everyone to show up on the first day. But I'm going to post an announcement after class. So what I do and why I have this set up here is because I'm actually recording the lecture and live streaming it. And so here we can see this is my YouTube channel. There we are, live streaming. And so I do that so just in case you can't come, right, you can join in from home. It's on YouTube, join in the chat, say hi so I know you're there and alive and functioning. But that's one way to join, but then it's also, of course, available for viewing and your enjoyment right after. So, and again, I'll post the link so you can find it. But a lot of students have told me that they found it really helpful to review and study with these videos. And again, you know, if you miss class, I have that there. And I try really hard to always do it, but you know, I can't make guarantees, but hopefully I will always upload the lecture. And that usually happens, again, minus any technical issues. All right, so I will post that. And so I will see the other half of you for lab on Wednesday. Make sure you wear closed-toed shoes and pants. And be careful with the holey jeans. So this week is probably okay if you wear holey jeans. But then as we get to like our flame test labs and kind of more dangerous stuff, you're going to want to make sure your pants don't have holes. Save those for non-lab days. All right, and then if you have any questions, I have office hours basically after every class period, or you can hunt me down. So I'm more than happy to answer questions. Yeah. Oh, and then grab homework, grab homework. So I'm going to put the homework just right here so you can grab it on your way out. Sorry, I forgot to distribute that. Yeah, and then the lab, if you want to get your lab for Wednesday, you're more than welcome to grab it and preview it. So I'll put the Wednesday lab down here as well. The Wednesday lab, Wednesday lab. And I'll go ahead and stop this stream.